In this poster we present a non-affinity based purification platform for neutral and basic IgMs. IgMs are antibody proteins that constitute large vesicles of pentamers and hexamers, and these types of molecules therefore have a very large molecular mass, so they're around 1,000 kilodaltons, and this is one of the separation challenges that is involved with IgM molecules. On the other hand, they're also having instability to low pH in some cases, so you can't go down with pH levels to values like 4 or even lower, and this also limits you in your ability for the purification. And next to IgM molecules, this purification platform is also relevant for other antibody-derived proteins like IgG fragments, single-chain FV fragments, also nanobodies and diabodies that you are having. So in general, this presented platform can be applied to a variety of molecules. And what we are showing here is first a capture step with a high capacity cation exchanger, which is followed by a polishing step with a very selective multimodal resin, the ceramic hydroxyapatite. And in figure 1 we are presenting a first capture development with the Nuvia S high capacity resin. In this case we were working with a constant pH of 5.0, and what you can see is a typical profile for this type of capture. So you have a lot of material in the flow through, and you get a peak maximum in the elution here that is followed by a small shoulder, and the SDS page nicely shows you that the peak maximum here contains the multimeric IgM in the top part of the SDS page lanes, but you also purify a lot of product and process related impurities, for example serum albumin and transferrin, which are between 50 and 70 kilodaltons in size there. So optimizing this step means that we go to a pH value that is 1.5 units below the PI of the IgM proteins that we were testing. And when you're doing it in that way, you can see that the profile in the chromatogram changes a little bit, so the maximum elution peak gets narrower, and you have a more pure product in the elution here. So you can see that the amount of process-related, also product-related impurities gets significantly lower, and you've got a better purity coming out of this elution. So we were then taking the elution pools from the Nuvia S runs and putting them onto the ceramic hydroxyapatite. Ceramic hydroxyapatite is a material that has two functionalities. The first one is a cation exchange functionality that is modulated by sodium chloride. The second functionality is a metal affinity that is modulated by sodium phosphate. And in this case, we were first trying to understand the elution behavior of the IgMs on the ceramic hydroxyapatite. We were doing runs in the presence of low phosphate concentration with a linear sodium chloride gradient. So this resulted in no elution. The IgM was coming off in the stripping step with phosphate, and we finally decided to do a linear phosphate gradient, which gave us a good elution of the IgM, and we could further optimize the polishing step by adding sodium chloride to the phosphate buffers, and in this case we get a very nice elution peak in the gradient elution there. There is also some other molecules coming off in the stripping, and when you're looking at the SDS page, you really nicely see that you have the multimeric IgMs here in the elution fractions. We did this for 3 different types of IgM molecules, and figure 4 here shows the reduced SDS page of these molecules, and in that case you can nicely see both the heavy chain band here at 75 kilodalton and also the light chain band of the IgM at 28 kilodaltons without any impurities that are process or product related. So in summary, we were able to present a platform process that is suitable for IgM molecules or IgE molecules, and also fragments that are derived from IgG antibodies by combining the capture with a high capacity cation exchange resin and the polishing step with a very selective multimodal resin, the ceramic hydroxyapatite type 240 microns that we used in this case.